Okay, good morning everyone. So today I'm going to present the paper named Learning Metapath-Based Context for Top-End Recommendation with Neural Core Attention Model. So this work is published in KDD last year. So firstly, I want to give an overview about the paper. Basically, this one is, oh, come on, the machine hangs. Okay. So the quick overview is the problem at hand is top-end recommendations, and the input we have is preference data, which come in the form of implicit feedback, and we have another type data. It's a graph data. So in this paper, they consider the heterogeneous information network. So what is the heterogeneous information network? Here is one example. For example, we have a user, movie, and D is the director and the attribute of movies. So those can be constructed as one heterogeneous information network. I call HIN for now. So HIN, this is one example of HIN. And the goal of this work is to introduce a model that can give better recommendations. And another goal is that to show some interpretability of the model, of the recommendations. So, first, I want to go through the HIN. There are some terminologies that we need to know. First is the path instances. So, each path instance is basically one path in the graph. So here we have, let's say, U1, M1, D1. This one is one path. We can have U2, M2, T1, and M1. It's another path, so on and so forth. So we have multiple path instances from the graph. So each path instances belong to one metapath. So what's metapath? Metapath is the type. Basically, each node here belong to one type. For example, all the user belong to a type of user. Movie, all the items belong to type movie. So let's say this path instance belong to this metapath, UMD. And the same, we have this path instance belong to UMTM, which is the user, movie, the type of movie, and another movie. So, so on and so forth. So we have path instances and metapaths. So what we are interested here is the metapath between each user and movie, because we want to recommend movie to user. So the set of all the metapaths from one user to one movie contains many path instances inside, and those set we call it metapath-based context, and we want to learn those contexts between the user and movie to improve the basically to learn the context between the user and movie to give better recommendations. So I start first with the embeddings. So those neural network models start with all embeddings. So I start with the first layer of the embeddings. So what we have here is user is one hot encoded, and basically we normally look up in the table to get the embeddings of user, XU. Similarly, we have the embeddings for items, YI. For between user and item, there are possibly we have multiple metapaths. So here is one example of metapath. Let's say UM, which is the length of 4, and for this metapath, we can have multiple path instances. So we can, one of the naive approach, we can randomly sample the path instances. For example, like deep walk, we can sample the path and on the graph. So here, another constraint is the path metapath. So we have the constraint of metapath, and then we can sample based on that metapath to have a bunch of path instances. And from those, we can have a CNN to learn basically to encode the information from these path instances. So easier to imagine here is each path instance here is like one sentence. So let's say we apply CNN for text. So each instance here is one sentence. Each node here is one word. Each word has their embedding. So basically here is a movie, user, movie, user, movie. So each one have their own embeddings. So we use CNN to encode each path instance. And each path instance here, after we feed through the CNN, then we can have embedding of that instance. So we have multiple instances. So here they apply a layer max pooling to pull all the path instances to have the final embedding for this metapath UM. Any question from this point?
The length is uniform.
The length. Basically, the advantage of CNN is that you don't need to worry about the length, because you can learn with the variant length, and then you do max pooling in the end, and then you get the representation of that sentence. So it's the same as what we do with the text. So we have multiple lengths. Basically, normally they do padding, and then they do pooling in the end to get the embedding. So this idea basically the same for text, and they apply here to get the embedding of this each instance here, and then they have the embeddings for the whole metapath with another pooling layer after that.
So the simple any path between the user and the movie.
So here is one metapath, so we can have multiple metapaths. Let's say we have two, then we can have another one, and then we repeat the process, and then we have this embedding for another metapath. So let's say between this user and item we have two metapaths, then in the end we're gonna have two embeddings.
So you have different CNN for different.
We have same CNN. We share CNN. The CNN, there only one CNN, but it's encode each metapath independently, and then in the end we're gonna have each embedding for each metapath. Okay. So at this point of time, we have user embedding, we have item embedding, and we have the embeddings for each metapath between user and item. And this is what we care for now. So first naive variant of this model is we have multiple embeddings for different metapaths between user and item. What we want is we want to pull some common embeddings from this set of embeddings. So the naive approach is that we can do averaging. So we can average over all these embeddings to get the one uniform embedding between user and item. So we call CUI here. And from this one, we can simply concatenate those three embeddings, and we learn multilayer perceptron after this feature to predict the score. Basically, it's the score how user U prefer item I. Basically, in the end, what we want is that we want to have this score for each user to all the items. Then we can rank, we can give the top end recommendations. So averaging is one approach. So what is better than averaging? What is better than averaging? Attention. So they call it path attention. So basically, the basic idea is that here, if we do averaging, we just put the same width for all the width above.
Better than average.
Well, that is what they gonna show in the result for this particular problem. So attention here is better than averaging.
Average attention.
So yeah, so the idea is that we want to involve user and item here to basically redistribute the width across this metapath. So some metapaths are more important for this pair of user and item, some are not. So how do they do the path attention here? So actually it's the two-layer of multi-layer perceptron to calculate the attention width for each metapath. So the first layer, they're gonna have the user embedding, the item embeddings, and the embedding of that metapath. And then they're gonna have the articulation here, and then after this one, they have another layer which gonna output the score for this user item and this path. And after that, they normalize it. Basically, it's softmax normalization, and they're gonna have the score for each metapath, and then they aggregate all the embeddings of the path into one CUN here, CUI here. So basically, instead of doing averaging, they do the path attention to have this CUI. So this is another variant of the model.
When you still averaging, right? You Just weighted average.
Yeah, it's weighted average, which is the attention. We normalize, we don't average. But do you want one? Any question? Any question? All right. So, okay, what can we do more? We already have path attention. We can do user attention. We can do item attention. So, what does it mean? So the basic idea is that after we have these embeddings between the path, they want to do another further step. This one I'm not sure it's good or not, but the idea is that they want to use this one to reweight the factors of user and reweight the factor of items. So the idea is like the beta u and beta I here is like a mask over the embeddings of user and over embeddings of items. So basically they try to reweight it for each dimensions. So they have another they have one layer of perceptrons. They're gonna project into the beta u and beta I here at the same dimensions of the user factor and item embeddings, and then they gonna do element-wise multiplication here to get the x tilde u and y tilde I. Yes, so at this point of time we have, this is the complete model of the one that is presented in the paper. We have embeddings layer, we have path attention, and we have user and item attention. So in the end, the final operation still stay the same with the concatenation between three types of features and an NLP to predict the score. Yes, any question? No more. Thank you. Very effective.
So what do the
you are the one who should ask. Okay.
what do the embeddings of the path supposed to capture?
What is the embedding of the path supposed to capture? Yeah. So for example, I can give one example like. Maybe the model recommends this movie to you because one of your friends watch. You share the same movie of one of your friends. Let's say the path is UM.
Okay.
So you and one of your friends share one of the same movie. Okay. So they recommend the movie that your friend watched to you.
Alright.
Or you, let's say attribute. Let's say the movie is drama movie. You like drama movie. And one of your friends also like drama movie, so you share this type, and then they recommend this movie from your friend to use. Let's say U, T, U, N, for example. So basically, those are from the heterogeneous network.
What is the T?
T is like type, for example, the type of movie. Yeah.
And each type also has its own embedding.
Yes, it has their own embedding. Basically, each node in the graph has their own embedding. So even each user, each item, each type, each each director, for example, the director of the movie, or maybe even character, some famous character have their own embedding, and then they're gonna learn from the.
Do you need to predefine how many types of metapaths that you can have?
You can predefine it. It depends on the data as well, like how many types of the nodes that you have in the graph. And in this paper, they only consider 3 or 4 the length of the metapath. They don't go to 5. They said that it's going to introduce noise, so because it's too long, so the dependency is not that strong, and maybe it's even more expensive. When you go longer, then you have exponential number of the paths, maybe, and then yeah. So for each part, you have to sample it independently, and then you will do an embedding for each type of metapath. In theory, you can do as much as you can. So there's one question here: is there a better way to sample the path instances? So at the beginning, we sample it randomly, basically based on constraint of the metapath at each node. We're gonna randomly sample the outgoing edges from that node to get the next node. So here they hypothesize that they can introduce a better way to sample the higher quality of the instances for that metapath. So what they do is they base on one of the approach for recommendation is SVD feature. So basically SVD feature is nothing but the metric factorization, the bias metric factorization plus the feature part. So the basic idea is that, for example, here is a recommendation between the user, item here is a song. So in the metric factorization, we only have the user and item itself. But here they introduce the feature. For example, here's the album of the song, the album of the song. So the preferences of user expressed toward the item I is not only toward the item I, but towards the album that the item I belong to, or even the singer that sing the song I, for example. So that's the basic idea of the SVD feature. And for this one, you can introduce as many as type of features that you want. Here you can have multiple type of feature comes from the item side, and you might have some of the other feature come from user side if you have. So that is the flexibility of the SVD feature in addition to the metric factorization. So they employed SVD feature to learn from the implicit feedback that they have. So the feature here, for example, the movie, right? So we have the type of movie, so one type feature. So you have the director of the movie is another type feature. So you can have different set of Q here, the Q factors here for the item side, and then you're gonna learn to predict the preference of the user to the item. So basically, it's one step before the neural network that they apply here. So they use SVD feature to learn from this network, and then after this one, basically each one gonna have their own embeddings on the graph, which is this Q. And for each path instances, they're gonna calculate the pairwise similarity between basically each consecutive node. So the U1 M1 and M1 D1, they sum it up and then they average it. So each path instance gonna have one the similarity score after this one, and they based on this one to rank the instances for that metapath. Yeah, maybe we need to give some intuition on this one.
How do you measure
How do you measure? They don't mention which distance they use, but it's possible both sides. They don't mention in the paper. I wonder as well which distance they use to measure the similarity.
Pairwise similarity between any two?
Pairwise similarity between each consecutive pair of the node in each instance.
Based on the SVD features?
Based on the feature that learned from SVD.
Averaging over
the number of the length, basically averaging over the length of the instance.
So how do I know that it's not just because of the SVD?
How do you know that it's not because of the SVD? Because they're gonna compare with this
average
after that.
In this one?
Yes, basically this one one of the baseline of the model. So this one actually is one baseline. Actually, after you learn SVD, you already can recommend based on the prediction.
So wouldn't the SVD use exactly the same set of features?
Wouldn't SVD use exactly the same set of feature, but this feature is going to be the initialization of the embeddings for the next model. So the next model is going to fine tune based on top of this feature. This is like pre-trained model for the next model.
But it's exactly the same features?
Exactly the same feature, yes.
That means they use exactly the same information?
Yes.
So what is the reason that the next one can be better?
What is the reason the next one can
I mean, you give them the same information.
You give them the same information. Okay, give the same information. So let me think about it. So this one is so first one is the same as uniformly sample, right? And the prediction is different. They have the notion of the metapath. This one doesn't have.
So, but what are the features then?
What are the features? The features
so the actor of a movie is a
let's
feature?
say, yeah, it's one type feature. Yeah.
the director of the movie is one type feature. The attribute of the movie is another type feature.
So it's just the indirection.
Yeah.
This one is just direct.
It's direct, basically the bilinear multiplication between the user feature and the sum of the other features. You're not afraid to ask questions, right?
Maybe I want to ask a lot more questions.
Okay. Any question on this part? All right. So learning, basically we already have the architecture of the model. So the final score is based on MLP from the concatenation feature, and they learn based on this by minimizing this negative log likelihood. And this is, like say, the user and the item I. Here is the positive, so they want this score to be positive. Basically, it's closer to 1, whereas this one they want closer to 0, where J is the negative item. Okay. So I quickly go through experiments. So for data set, they have 3 data sets. They have movie lens, they have last FM, and they have YEP. Those are the relations that they have from the data set, which can use to construct the heterogeneous information network. Then this is the number of the type of the nodes. So for each one, they gonna construct different type of the metapath. Let's say movie lens, they have 4 type of the metapaths. The last FM is the same, and the YEP they also have 4 type. So let's say for YEP here is a B is a business user. CA is the category that the business belong to, and the CI is the city of that business. For metrics and the baselines. So metrics, they use 3 ranking metrics to measure the performance of the recommendations. Precision at K, recall at K, and the ECG at K. Baselines, they have different set of baselines. The first 2, the blue one, are the model that's purely based on the collaborative filtering. The first one is the K nearest neighbor based on items. The second set is basically based on the metric factorization. The orange one based on not only the implicit feedback but based on the graph, basically the information from the HIN network. These are basically the state of the art, and Truong is going to present this later. For the proposed model, they have 4 models. The first one, basically this this is the averaging one. The averaging one, the one with the path attention, and the complete model with the path attention, user, and item attention. The random one is to indicate, to show the improvements over the better way to sample the path instances. So random means that you don't have the SVD feature part. You don't learn beforehand to rank the path instances, but you just randomly select the instance. So first, for the recommendation performance. Okay, quick look. The final model outperforms the rest of the models. So this is the best performance over the baselines. You see the gradual improvement over the proposed model with the random, then average, then the path attention, and then the final model. So the star here to indicate the significance, the t-test significance with the p-value is 0.01 and over the baseline, over the best baseline. Basically, is your model. And the same trends are observed for the last FM and the YEP dataset. So here I only show 1 table. So we have another 2 tables for the last FM and the YEP datasets. They do the experiment over the gold star problem, and they show, basically they split the data. Here the percentage here are the training percentage, the training data. So 20, 40, 60, 80, and these numbers are the improvement over the BPR model on precision at 10. So we're going to see when the data is very sparse, we're going to see the improvements. Basically, we benefit more from the network, and then we see the big improvement over the BPR model, where we have more data, then the BPR can learn quite well. Then the improvement is not that big anymore. So the same for Yap. For Metapath-Based, basically they try to measure which type of path, which type of metapath actually important. So here is movie length. We have 4 types, and then basically they just plot the attention, the distribution of the attention over the metapath across all the data set, and they see, for example, this UMGM is the more important than the other 3. For the last FM, they may see this one UUA and the UATA is more important. They do the same for the YAP. The contribution of metapath, they incrementally add in the type metapath. So at the beginning, they don't have any type of metapath. So this is the performance of the model compared to NeoMF is the state of the art for the basically correlative filtering. And this one, they add this metapath, they add this one, they add this one, and they add the last one. So this you see the improvement increasing when you have more type of the metapath. They show one example to show the interpretability of the model. Basically, they have this user, and they try to interpret how the model recommend these 2 movies to this user. So from this side, we can show the attention score over the type of metapath between this user and this movie. And the the highest score is UM. So basically, this movie is recommended to this user because one of another friend. And then they see is in the data, at least 5 friends of this one have watched this movie before. And even UUM is also high score here because they go through some of the user and they go to that movie. Another example here is this movie is recommended to this user, and this is drama movie, and actually it's the type, the favorite genre of this user. So you have the UMGM, G is G. So this is one example that they show in the paper.
So why do you assume U782 is a guy? From the movies, it doesn't look like that.
I don't, but the avatar looks like.
Oh, this is from the paper?
This is from paper. I don't created this one.
Okay.
Yeah, so I come to the conclusion of the work. Basically, there are 3 points. First, they introduced the core attention mechanism for the top-end recommendation in the HIN. They have introduced the priority-based sampling technique to sample better quality of the past instances compared to previous works. And they have extensive experiments to show both the recommendation effectiveness and the interpretability of the model. So, yeah, thank you.
Unfortunately, we have no time now, so we have to move on to Truong for the briefing.
Okay.
You can hold your questions until after.
Lỗi rồi. Cái file mình bị lỗi. Mở lại cái download.
Sorry, there's some problem. I need to resend.
Dropbox.
No, I didn't.
No Dropbox. Okay, it's the file.
So give me a minute.
The file's corrupted. I hold this.
So wait, can I ask question?
Yeah. But what is setting?
I'm holding this one.
Actually, I'm curious. Do they mention how they sample the parts given the feature SVD features? Isn't any efficient way to do that kind of sampling?
As I understand, I guess they sample all possible paths.
and then they compute the score and then the rank. So they take
All
like
possible
top K.
passes.
Yes, for each meta path
Okay.
from this user to that item. So then they have the score and then the rank, and they get the top K, for example.
So they have to have all the possible paths.
I guess
For-
maybe not a lot between user and item.
Yeah. So it's gonna be like number of user square times number of items square. Right?
Maybe more than that, because you go
Yeah.
through the I mean, if you actually have connection in the network, right?
Yeah.
But I guess the network is sparse.
Yeah, but it's not scalable, right? You have to enumerate all the possible paths. Between
Actually, this one gonna be slower than the random one, right? Because random one you
Yeah,
don't
yeah,
care.
yeah, correct,
But
yeah.
this one you need to rank. So
So
the basic idea is that you have all the possible instances and then you rank to get the